Welcome! In this video, we'll be solving LeetCode problem number 1315, sum of nodes with even-valued grandparent. This problem involves tree traversal and is a great opportunity to practice working with binary trees. We'll explore the problem requirements and walk through an effective approach to solve it. Let's dive in. In this problem, we are working with a binary tree, and the goal is to determine the sum of the values of nodes that have an even-valued grandparent. A grandparent in the context of a binary tree is simply the parent of a node's parent, provided that both exist. If no such nodes with even-valued grandparents are found, the result should be 0. The input to the problem is the root of the binary tree, which is represented as a tree node object. Each node in the tree contains a value, as well as references to its left and right child nodes, if they exist. The output will be a single integer, representing the total sum of all nodes that meet this condition. This problem requires us to navigate the tree and evaluate nodes based on their grandparent's value, so understanding the structure of the tree is critical. To better understand this problem, let's consider the first example. We are given a binary tree where the root node has a value of 6, and its children are nodes 7 and 8. These child nodes themselves have further children, forming a multi-level tree. In this example, the even-valued grandparent 6 has grandchildren with values 2, 7, 1, and 3. Adding these values gives us a sum of 13. Additionally, the even-valued grandparent 8 has grandchildren with values 9, 1, and 4, which add up to 14. Meanwhile, the odd-valued grandparent 7 does not contribute to the sum. Combining the sums from the two even-valued grandparents, the total is 13 plus 14, resulting in an output of 18. This example highlights how we identify and sum the grandchildren based on their grandparents' value. Now let's look at another example where the tree is much simpler. Here, the root node has a value of 1, with two children, 2 and 3. In this case, there are no nodes with an even-valued grandparent because the root node does not have a grandparent itself, and its children do not have any further descendants. As a result, the output is 0. Similarly, in another example, we have a tree where the root node has a value of 4, with two children, 2 and 9. Although the root node is even-valued, it does not have any grandchildren. Since there are no nodes in the tree that satisfy the condition of having an even-valued grandparent, the output again is 0. This demonstrates that simply having an even-valued node in the tree is not sufficient, it must specifically be a grandparent for its grandchildren to contribute to the sum. To ensure our solution is robust, we must consider a few constraints and edge cases. First, the binary tree can contain up to 10,000 nodes, so the algorithm must be efficient enough to handle large trees with multiple levels. Additionally, the values of nodes are integers between 1 and 100, which means we don't have to handle negative or very large integers. Edge cases include trees with a single node, where the output is always 0 since no grandparents exist, and trees where all nodes have odd values, which means there are no even-valued grandparents to consider. Sparse trees, where nodes are missing at various positions, should also be handled properly, ensuring that the algorithm adapts seamlessly to irregular structures. Finally, for deeply nested trees, it's important to manage recursion or iteration carefully to avoid exceeding memory limits or running into stack overflow errors. To solve the problem of summing nodes with even-valued grandparents, we first considered a brute force approach. The intuition here is straightforward: traverse the binary tree and, for each node, check if its grandparent exists and whether its value is even. If the condition is met, we add the node's value to a running sum. To implement this, we use a recursive depth-first search, or DFS, to visit every node. During the traversal, we keep track of each node's parent and grandparent. At every step, we check whether the grandparent's value is even before updating the sum. This approach has a time complexity of O(n), where n is the number of nodes, because we visit each node exactly once. The space complexity is O(h), where h represents the height of the tree, due to the recursive call stack. However, this approach has a drawback: maintaining references to both the parent and grandparent can make the logic cumbersome, especially in larger or more complex tree structures. While straightforward, it becomes less elegant as the tree grows in size or depth. Next, we explored an iterative DFS approach. The key idea here is to simulate the recursive DFS process using an explicit stack. In this method, we store each node along with its parent and grandparent in the stack for processing. To implement this, we initialize a stack with the root node, and we set both its parent and grandparent to none. As we iterate through the stack, we check whether the grandparent's value is even and, if so, update the sum. The time and space complexities remain the same as the brute force approach, n, time to visit each node once, and h, space due to the stack size, which corresponds to the tree's height. The main advantage of this approach is that it avoids recursive function calls, which can be beneficial in very deep trees. However, managing the stack manually can become verbose and error-prone, especially when handling the relationships between nodes. We then refined our exploration further with an optimized recursive DFS approach. This approach is similar to the brute force method but improves state management by directly passing the grandparent's value to child nodes during recursion. This removes the need to explicitly track parent and grandparent references, streamlining the logic. The implementation involves passing the current node's value as the parent and the parent's value as the grandparent to the child nodes. With each recursive call, we check if the grandparent's value is even and update the sum accordingly. This method retains the same n, time and h, space complexities but is much cleaner and easier to read. It eliminates the verbosity of the iterative stack management and the additional state tracking of the brute force approach, making it a highly efficient option. We ultimately selected the optimized recursive DFS approach because it provides a clean and efficient solution to the problem. The core idea is that we only need the grandparent's value to determine whether to include the current node's value in the sum. By passing this value directly during recursion, we simplify state management and avoid the need for additional data structures. The key insight that led to this choice is the relationship between a node and its grandparent. The grandparent is always 2 levels above the node in the tree. This means we can track the grandparent's value simply by passing the parent's value to the next level of recursion. Additionally, the even-valued property of the grandparent simplifies our logic to a straightforward modulus check, such as grandparent %2 = 0. This observation allows us to focus only on the values that matter. Lastly, by passing the grandparent's value directly during recursion, we eliminate the need for cumbersome state tracking with extra variables or structures. This makes the code not only more efficient but also significantly cleaner and easier to maintain. When comparing the approaches, we see clear trade-offs. The brute force method, while intuitive, requires explicit tracking of parent and grandparent references, which makes the code less readable and harder to maintain. On the other hand, the iterative DFS approach avoids recursion but introduces the complexity of manually managing a stack, which can be error-prone and verbose. The optimized recursive DFS approach strikes the ideal balance between these extremes. It is both efficient and simple, leveraging Python's call stack to handle recursion naturally and passing only the grandparent's value to streamline state management. This makes it cleaner and easier to implement without sacrificing performance. Overall, the optimized recursive DFS approach is the best choice for this problem, as it offers a solution that is both elegant and effective. In this problem, we are tasked with finding the sum of all nodes in a binary tree whose grandparent nodes have even values. A grandparent node is essentially the parent of a node's parent. If a node does not have a grandparent, it is ignored. To solve this, we need to traverse the tree while keeping track of each node's parent and grandparent. Depth-first search, or DFS, is an ideal choice for this task because it allows us to efficiently visit each node and its ancestors. As we traverse, we will use recursion to propagate the parent and grandparent information down the tree. This ensures that at every step, we know whether the grandparent exists and whether its value is even, which is the key condition for including a node's value in the sum. Let's define the steps to implement this approach in detail. The recursive function we'll define for DFS will take 3 arguments: the current node, its parent, and its grandparent. The base case is straightforward. If the current node is null, we return 0 because there's nothing to contribute to the sum. In the recursive case, we check if the grandparent exists and whether its value is even. If both conditions are true, we add the current node's value to our sum. Then, we continue the recursion for the left and right children of the current node, updating the parent and grandparent values as we go. This way, each child node gets the correct context about its parent and grandparent. To calculate the result for each node, we combine the value of the current node, if applicable, with the sums returned from its left and right subtrees. This aggregation ensures that every node in the tree is processed appropriately, contributing to the final result if its grandparent meets the condition. By passing the parent and grandparent values recursively, we keep the implementation simple and avoid the need for additional data structures to track ancestors. This efficient propagation of context allows us to focus only on nodes with even-valued grandparents, skipping unnecessary computations for odd-valued ones. The algorithm has a time complexity of O(n), where n is the total number of nodes in the tree, since each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, because of the recursion stack. The tree node structure we work with includes a value, a left child, and a right child. The recursive call stack is used to maintain the state of the current node, parent, and grandparent during traversal. Here's the Python implementation of the algorithm. We define a helper function DFS within some even grandparent. This function computes the sum at the current node, recurses for the left and right children, and returns the aggregate sum. The main function initializes the process by calling DFS on the root node with none values for the parent and grandparent. The implementation relies on a few key operations. First, the condition grandparent %2 = 0 ensures that we only include nodes whose grandparent has an even value. Second, the recursive calls DFS, node.left, node.val, parent, and DFS, node.right, node.val, parent, allow us to traverse the entire tree while updating the parent and grandparent context. Lastly, the sum calculation aggregates the contributions from the current node and its left and right children. The algorithm handles edge cases effectively. For example, if the tree is empty, the function immediately returns 0. For trees with 1 or 2 levels, nodes without grandparents are ignored, as required by the problem. Additionally, if all grandparents in the tree have odd values, the result will naturally be 0, since no node will meet the inclusion criteria. To illustrate this, let's walk through an example binary tree step by step. In this example, the root node is 6. Since the root has no grandparent, its value is skipped. The same applies to its immediate children, 7 and 8, as they also lack grandparents. However, when we move to the grandchildren, nodes 2, 7, 1, and 3, we see that they all have 6 as their grandparent, and since 6 is even, their values are added to the sum. We continue this process recursively, including deeper levels of the tree. For instance, node 9 is a descendant of 2, and node 4 is a descendant of 3, both are included because their grandparent 6 is even. After summing all contributing nodes, the final result is 2 plus 7 plus 1 plus 3 plus 9 plus 4, which equals 26. This example demonstrates how the algorithm efficiently identifies and sums the values of nodes with even-valued grandparents while skipping others. This implementation solves the problem of summing all nodes in a binary tree whose grandparent node has an even value. ###explanation. 1. TreeNode class. The TreeNode class is provided as part of the problem for representing each node in the binary tree. Each node has a value, val, a left child, and a right child. 2. Solution class and main function. The SumEven grandparent method is the main function for solving the problem. It takes the root of the binary tree as input and returns the total sum of nodes with even-valued grandparents. 3. DFS helper function. This function is a depth-first search, DFS, that traverses the tree recursively. It accepts 3 arguments: the current node, its parent, and its grandparent, The base case checks if the current node is none. If so, it returns 0 since there's no value to add. 4. Grandparent value check. If the grandparent exists and its value, grandparent.val, is even, the current node's value is added to the total. 5. Recursive calls. The function makes recursive calls for the left and right children of the current node while updating the parent and grandparent references appropriately. 6. Initial call. The DFS is initiated with the root node, and both the parent and grandparent set to none since the root does not have a parent or grandparent. ###edge case handling. If the tree is empty, root is none, the function correctly returns 0. Nodes without grandparents are naturally ignored since the grandparent argument will be none. ### complexity. Time complexity, the algorithm visits each node exactly once, so the time complexity is O(n), where n is the number of nodes in the tree. Space complexity, the space complexity is O(h), where h is the height of the tree, to account for the recursion stack. This solution is efficient, clean, and handles all edge cases correctly. To solve the problem of summing nodes with even-valued grandparents, we first define a tree node class to represent each node in the binary tree. Each node contains an integer value, a reference to its left child, and a reference to its right child. We provide multiple constructors to handle different initialization scenarios, whether it's an empty node, a node with just a value, or a node with both value and child references. Next, in our solution class, we implement the main method SumEvenGrandparent. This method starts the process by calling a helper function, DFS, which stands for depth first search. The DFS function is designed with three parameters: the current node, its parent, and its grandparent. This setup allows us to track the relationships between nodes as we traverse the tree. Notice that the first condition in the DFS function checks if the current node is null. If it is, we simply return 0 since there's nothing to process further for this branch of the tree. Now, within the DFS method, we initialize a variable called total to accumulate the sum of node values that meet the given condition. Specifically, if the grandparent node exists and its value is even, we add the current node's value to total. This is achieved with a simple check on grandparent.val modulo 2. After checking the current node, we proceed to recursively call DFS for both the left and right child of the current node. Each recursive call updates the parameters to reflect the new relationships. The current node becomes the parent, and the parent becomes the grandparent for the next level of recursion. Finally, we return the total sum accumulated for this branch of the tree. By combining these recursive calls, we ensure that the entire tree is traversed, and all nodes with even-valued grandparents are considered in the final sum. Here, we begin by examining a binary tree where some nodes have even-valued grandparents. The process starts with a depth-first search, or DFS, beginning at the root node, which is 6. Since the root has no parent or grandparent, there's no contribution to the total sum at this point. Moving to the left child, node 7, we set its parent to 6 and the grandparent to none. Again, there's no contribution to the sum here because the grandparent is still absent. Then, we explore the left child of node 7, which is node 2. Now, the parent is 7, and the grandparent is 6. Since the grandparent, 6, is an even number, we add the value of node 2 to the total sum. This brings the running total to 2. From here, we continue exploring deeper into the left subtree of node 2. At node 9, the parent is 2, and the grandparent is 7. Since the grandparent, 7, is odd, we don't add anything to the total sum, and it remains unchanged. From node 9, there are no further children, so we backtrack to node 2 to check its right child, which is none. With no nodes to process there, we return to node 7 and explore its right child, another node with the value 7. Here, the parent is 7, and the grandparent is 6. Because the grandparent, 6, is even, we add the value of this node, 7, to the total sum. Now, the sum becomes 7. Next, we return to the root node, 6, and explore its right child, node 8. At this point, the parent is 6, and the grandparent is none, so no contribution is made to the total. Then, we explore the left child of node 8, which is node 1. With a parent of 8 and a grandparent of 6, we see that the grandparent is even, so we add 1 to the total, making it 1. Finally, we move to the right child of node 8, which is node 3. The parent is 8, and the grandparent is again 6. Because the grandparent is still even, we add 3 to the total sum, bringing it to 3. Adding all the contributions together, 2, 7, 1, and 3, we get a final output of 13 for this example. Now, let's analyze a simpler case where the binary tree has no even-valued grandparents. The root node is 5, and it has 2 children, 3 and 9. Starting the DFS at the root, we find that no grandparent exists, so the total sum remains 0. Moving to the left child, node 3, the grandparent is still none, so the total remains 0. Similarly, for the right child, node 9, there's no grandparent, so no value is added to the sum. Since there are no further nodes to traverse, the final output for this tree is 0. Next, we consider an even simpler tree with just a single node, 2. In the single node tree, the DFS starts and ends at the root itself, which is node 2. There's no parent or grandparent present, so the total sum remains 0. This gives us a final output of 0 for this example. Now, to summarize the algorithm, we use a DFS approach to traverse the tree while keeping track of the current node, its parent, and its grandparent. Whenever a grandparent exists and its value is even, we add the current node's value to the total sum. This approach ensures that every node is visited, and the sum is calculated accurately according to the problem's requirements. The time complexity of our solution is O(n), where n represents the number of nodes in the binary tree. This stems from the fact that the depth-first search algorithm visits each node exactly once. To understand this, consider the operations performed at each node. First, we check whether the grandparent node exists and if its value is even. These are constant-time operations. If the conditions are satisfied, we add the node's value to the total. Additionally, we make 2 recursive calls for each node, one for the left child and one for the right child. However, since each node is visited only once throughout the traversal, the total number of recursive calls is directly proportional to the number of nodes in the tree. As a result, the overall time complexity is O(n). The space complexity of our solution is determined by the memory used by the recursion stack during the DFS traversal, which is O(h), where h is the height of the binary tree. Let's break this down. In the worst-case scenario, such as when the tree is completely unbalanced and resembles a linked list, the recursion stack could grow to a depth equal to the total number of nodes, resulting in O(n) space. On the other hand, in the best-case scenario, where the tree is perfectly balanced, the height of the tree is O log n, and the recursion stack space is reduced accordingly. It's important to note that no additional data structures are employed outside the recursion stack, so the auxiliary space remains constant at O(1). Therefore, the overall space complexity is O(h), which reflects the height of the tree. Let's compare the optimized DFS approach with a brute force method. A naive brute force solution might involve traversing the tree to identify all grandparent nodes first and then performing additional traversals to sum the values of their grandchildren. In the worst case, this could result in an O(n)² time complexity due to repeated traversals of overlapping parts of the tree. In contrast, the optimized DFS approach improves this significantly. By passing parent and grandparent references as arguments during the traversal, we eliminate redundant computations and ensure each node is visited only once, achieving an O(n) time complexity. When analyzing different scenarios, we see that in the best case, a perfectly balanced tree results in a recursion stack depth of O log n. For a moderately balanced tree, the depth falls somewhere between O log n and O(n). In the worst case, with a completely unbalanced tree, the stack depth is O(n). Across all cases, the time complexity remains O(n). The mathematical basis for our time and space complexity lies in the structure of the DFS traversal. Each node in the tree is visited exactly once, which justifies the O(n) time complexity. The space complexity, on the other hand, depends on the maximum depth of the recursion stack during traversal. By directly passing parent and grandparent references as we recurse, the algorithm avoids redundant calculations that would otherwise arise in a brute force approach. This optimization ensures that the solution is both efficient and scalable, achieving the best possible performance given the constraints of the problem. When solving this problem, one of the common mistakes to watch out for is incorrectly checking for grandparents. A node's grandparent might not always exist, and if you try to access its value without verifying its existence, you'll encounter a none-type error. To avoid this, always ensure that null checks are in place before accessing the grandparent's value. Another pitfall is double-counting nodes. If a node has multiple even-valued grandparents, its value should still only be added once to the sum. Structuring your logic to avoid revisiting or double-counting nodes is key. Lastly, inefficient traversal can be a problem if you use a brute force approach, leading to redundant checks and greater than optimal time complexity. Using a traversal method like DFS or BFS while tracking parent and grandparent nodes avoids these inefficiencies and ensures cleaner, faster execution. Another common issue arises from confusing parent and grandparent relationships. It's easy to accidentally treat a parent as a grandparent or vice versa, which can lead to incorrect sums, especially in edge cases like shallow trees. Clear variable names, such as parent and grandparent, and careful tracing of relationships can help prevent this mistake. Additionally, it's important to handle edge cases properly. Examples include trees with only a single node, trees that lack even-valued nodes entirely, or deep unbalanced trees. Failing to account for these scenarios can lead to runtime errors or incorrect answers. To address this, always include comprehensive test cases that cover both minimal and maximal input configurations, ensuring your solution is robust across all scenarios. From an interview perspective, this problem is an excellent example of tree traversal with state tracking. Many questions involving parent-child relationships or ancestor conditions require you to maintain additional state during traversal. Here, tracking the values of a node's parent and grandparent during a single traversal is key to solving the problem in an optimal O(n) time complexity. Interviewers might also extend this problem, for instance, by asking for the sum of nodes with odd-valued great-grandparents or even generalizing the solution for arbitrary ancestor depths. Be prepared to explain trade-offs between approaches as well. For example, while DFS with recursion or a stack is often more memory efficient for this problem, BFS might be preferred in scenarios requiring breadth-first guarantees, even though it typically uses more memory. This problem also connects to a number of related problems that you might encounter. For example, problem number 1123, lowest common ancestor of deepest leaves, focuses on tree traversal and ancestor relationships, making it a useful practice problem. Another is problem number 865, smallest subtree with all the deepest nodes, which involves tracking depth during a DFS. Similarly, problem number 1022, sum of root to leaf binary numbers, emphasizes recursive tree traversal with value accumulation, and number 1448, count good nodes in binary tree, challenges you to maintain state during traversal by tracking the maximum value seen so far. Practicing these problems will strengthen your understanding of tree traversal patterns and state management, which are critical for solving this class of problems. When considering alternative approaches, recursive DFS with state tracking is a common choice. By passing parent and grandparent as parameters, this method is simple, intuitive, and has minimal memory overhead. However, it might lead to stack overflow issues for very deep, unbalanced trees. Another option is iterative DFS, which uses an explicit stack to simulate recursion while tracking parent and grandparent nodes. This avoids recursion depth limits, making it suitable for deeply nested trees, but it can be slightly more verbose and less intuitive. Finally, iterative BFS with a queue is another viable approach, especially when level order traversal is required. While it ensures breadth-first guarantees, it tends to use more memory compared to DFS due to the queue storage of multiple nodes at each level. Each method has its pros and cons, and the best choice depends on the specific constraints and requirements of the problem you're solving. Great job! We've successfully solved the problem using an efficient approach. We reviewed the algorithm, its time and space complexities, and key concepts like tree traversal. Keep practicing similar problems to strengthen your skills. Don't forget to like, subscribe, and share. We'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!